So we're gonna do Unit 4 today. Um, we're gonna do 4.1 and 4.2 sequences and infinite series. Let's start off with the sequence. So what is a sequence? A sequence is a list of numbers in a specific order. Each number is called a term, an, of the sequence, and the subscript give its place in the line. So for example, A1, 1, A2, 2, 3, and all the way up to AN. Term before an is an minus 1. Notice how it's in the bottom corner here. The term after an is an plus 1, or plus 1 again is that bottom corner right there. The sequence can be written like this, or is denoted like this, or like this, and starts at 1 unless otherwise stated. So keep that in mind, especially because I've noticed that in some of your homeworks online, they're going to trick you with the notation of when it starts. So just keep that in mind, okay? All right, example one. Find the first four terms of this series. So this series has three parts. It has this part with n, it has this part with n, and it has this part with n. So really, we're taking the simplified expression of this fraction. So let's start off with the reds. So this is -1 to the nth power. Well, n is 0. So that's just going to be 1 right away. N is 1. For n is 1. So that means it's going to be -1. N is 2. So that means -1 times -1, which is back to positive. And then n is 3. So -1 to the power of 3. So we start here. We're going to go, okay, so we start with a negative, positive, negative. So negative. Then this expression says n plus 1. So n is 0. 0 plus 1, 1. 1 plus 1, 2, 3, 4. And you get the idea here. The last one is not too tricky, but it's definitely, we have to pay attention to it just a little bit more. It's 3 to the power of n. So when n is 0, that's just going to be 1. When n is 3, that's going to be, n is 1, that's going to be 3. When n is 2, that's going to be 9. And when n is 3, so it's 3 times 3 times 3, which is 27. The simplified version of all of this is 1, -2 over 3, 3 over 9, which we can tend to simplify to 1 over 3, and then -4 over 27. So this is just an idea of how to, I need to try on how to layer this out. Now, for the next part, we're going to also talk about factorials. So what's a factorial? Factorial of a non-negative integer written as n exclamation point, n factorial, is defined by a recursive formula. You first start off with 0 factorial being equal to 1. And then you say n factorial is n times the previous factorial. So for example, 0 factorial is 1. 1 factorial is 1 times 0 factorial, which is just 1 times 1, which is 1. 2 factorial is 2 times 1 factorial, so 2 times 1 factorial, which is 1, 2. 3 times 2 factorial, so that tells me 3 times 2, which is 6. Now, you would think this guy is 12, but it's not 12. 4 times 3 factorial, 4 times 6, because we said 3 factorial is actually 6, which is 24. 5 times 4 factorial, which is 24, which is 120. And then 6 times 5 factorial, so 6 times 120. I'm not going to do that math. I'll do that math out loud just real quick. So it's going to be 720. Then 7 times 720. That's going to be here. This I'm just going to copy and paste. Actually, I didn't even do it because I was lazy. All right, let me put on the calculator. 7 times 720 is 5,040. 8 times 7 factorial is 8 times 5,040. So we got about 40,000 numbers. Now let's deal with some arbitrary ones. What is n plus 1 factorial? Well, we know this is technically n plus 1 times 1 less. So times n factorial. And technically you can expand this into n plus 1 times n minus 1 factorial. And you can keep expanding this last factorial part until you get n plus 1 times n times n minus 1 times n minus 2, and you would keep going until you have 1. And that would be your answer. Alright, over here, similar vibe. You technically start off with 2n plus 2 times 2n plus 1 factorial, which can be expanded to 2n plus 2, 2n plus 1, times, keep forgetting to do the actual dots, 2n factorial, and so on. So, an example of a series using factorials. Let an be equal to 5 to the power of n times n factorial. And an plus 1 to be that same thing, but just with instead of n is n plus 1. Find the quotient. Find a subscript n plus 1 divided by an. First thing I'm going to do is I'm going to go ahead and write this just out. 5n plus 1 times n plus 1 factorial over 5n times n factorial. I'm going to start with this first. This is probably the simplest. Just simplifying power. So 5n plus 1 minus n times this fraction, n plus 1 factorial over n factorial. That's just going to be 5. And here for this factorial, we know we can expand it to be n plus 1 times n factorial. So that's going to cancel out, and we're left with the result of 5 times n plus 1. All right. So this is just sort of, technically pre-cal mentions this towards the very end, but it's just good to go over this overall. It's a fun little puzzle at this point where it's very, hold on, let's sneeze. Okay, hopefully I successfully muted myself. If I didn't, sorry. Um, at this point, it's kind of like a puzzle. We're just playing with the numbers and their patterns and how we see them. But it's important to note that we are increasing the difficulty from here. So now we're going to talk about limits of these sequences. If the limit of a sequence, so if we take n to go to infinity of this sequence exist, the sequence converges. We say the sequence converges. If the limit of that sequence as we go to infinity does not exist, then the limit diverges. So keep that in mind. This is going to be important terminology from here on out. Sequence converges, the sequence diverges. Let's go over here. Identify whether the sequence converges or diverges. Okay. Well, we can see here that this number is getting smaller. And we could even give it a label. We can say an is definitely just 1 over n squared. Using that, this is just going to be 1 over 1. We have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc. And we know if we take the limit as n goes to infinity of the expression 1 over n squared, we would call this bottom heavy. And we reviewed it a little bit, and if you took my Cal 1 class, you saw that bottom heavy functions, their limit goes to 0. How about cosine of n pi? Well, cosine's a bit trickier, but we know that cosine typically behaves in this up and down format. It doesn't really have a limit. Here, we also see that this doesn't help us at all. It just puts n in terms of pi, which really just shifts the graph a little bit, but it's still making the same loop. So the limit as n goes to infinity, regardless of cosine of n pi, can really be technically rewritten as cosine of infinity, since we know that n pi, that's going to still go to infinity. And cosine of like an ever increasing term, that limit does not exist. So this is obviously the informal notation, sort of just like as we're working along it. But you could even just like politely skip this and just jump straight into here because we know this is gonna go to just up and down, not without a bound. Let's do some special sequences. The sequence denoted 1 over n to the power of p for all of these converges to 0 if p is positive and diverges if p is negative. So example, we see with 1 that it's just going to be keep going, and we could even label it as 1 over n since p is 1. And we know that this is just going to be as a limit. Again, bottom heavy, it's going to go towards 0. But p is negative 1. How about that? Well, that technically means that we can rewrite these as 1, 2, 3, 4, 5, etc. So that just tells me that this number is just going to keep increasing. It's a very trivial example about how this is going to go towards infinity. And that limit does not exist. So therefore, it is divergent. Okay, convergent, divergent. Convergent, divergent. A sequence of r's just being not multiplied, being taken to a power. So r1, r2, r3, or I should say r to the power of 1, r to the power of 2, r to the power of 3, excuse me. Converges to 0 if and only if the absolute value of r is less than 1. It diverges if the absolute value of r is greater than 1. So, letting p be positive, let's wrap up some ideas. First, we see as x goes to infinity for this setup that it's going to go towards infinity. Cosine, again, just squiggles, so goes towards, sorry, so it does not exist. ln, we know that one's just going to go towards infinity, and so this exponential, by the way. Then we have the square root. It's still a positive power, so therefore it goes towards infinity. Arctangent, again, while this is like a technicality, we see that for arctangent, it's going to go towards 1. And then for 1 over x to the p, that technically makes it to where p is negative. Or you could even from here just think about the bottom heavy portion, so it's going to be 0. However you want to think about it. And then exponential, similar vibe where we know that this can be written as e to negative x. So you're actually going towards negative infinity if you think about it, which that will be 0. Okay. Um, Okay, so let's go ahead and do this example. Example 4. Does the sequence converge or diverge? So we have 1 over square root of n. And for this, um, we're just gonna do basic applications of limits. Again, just a friendly reminder for all of these, we care if it converges or diverges based on if its limit exists or does not exist. If it exists, it converges. If it does not exist, it diverges. Start here. Okay, so this, you could do it if you want to, but you can rewrite 1 over n to the power of 1/2, which here you should see, okay, that degree is bigger than the degree on the top. So it's bottom heavy, so it's going to go towards 0. Here we have a copy and pasted of this, so we know that that's going to go towards 0 for similar logic. Here we have what's called a balance equation. So the expression on the top has the same degree as the expression on the bottom. They're both with degree 2, because the highest power in both the top and the bottom is 2. So that means we could just take their coefficients, and we should just have that be our limit, 4 over 5. You could have also acknowledged that this and this both have a limit of infinity. So you could use the L'Hopital's rule and get, what is the derivative of that? 8n, that zeroes out, and then you have over 10n minus 7. The limit as n goes towards infinity is still infinity over infinity, which lets you use L'Hopital again, and you would have 8 over 10, which simplifies to 4 over 5, which is what our answer was. So you can either treat as a balanced question or as using L'Hopital. Then, for question number 4, you see the degree of the bottom is greater than the degree of the top, so therefore, again, we have another bottom heavy. And that answer is 0. So again, for all of these, that's to imply that the sequence converges, because the limit exists for all of these. So all of these, again, are convergent. All right. Another way we're going to play with numbers is integer partitions. An integer partition of a number is a way of writing that number as a sum of positive integers, including ignoring the order. So, for example, what's all the way we can write 1? Well, just 1. 1. And you just count that, and that's going to be 1. How about here? 2. What's all the ways we can write 2? Well, we could write 2, or we could write 1 plus 1. I can't think of any other way to write 2 as a sum of positive integers, keep that in mind. So that's going to be 2. There's 2 partitions of 2. 3 has 3. It has 1 plus 2. And it has 1 plus 1 plus 1. Again, the order doesn't matter. So 2 plus 1 is not anything different. So it's just going to have 3. You have 4. You have 1 plus 3. Then you have 1 plus 1 plus 2. Then you have 1 plus 1 plus 1 plus 1. And then now I'm going to jump to 2. You have 2 plus 2. And then that's it. So count them, you have 5. Then for 5, you have 5. You have 1 plus 4. 1 plus 1 plus 3. 1 plus 1 plus 1 plus 2. And then you have 5 ones. I'm going to do 2 now. 2 plus what? 3. And then you can split up the 2. No, wait, hold on. Oh, yeah, you can split up the 2 into 2 plus 2 plus 1. And it's going to be 2 plus 7. This gives us a sequence. Each term answers the question. How many ways can we write n as a sum of integers? Alright. 4.2, an infinite series. An infinite series is the sum of infinitely many terms of a sequence. For example, if an is a sequence, the infinite series can be written as a1 plus a2 plus a3 plus dot dot dot, and it's either notated with this s or with this actual sigma notation, where n goes from 1 to infinity. And again, I'm telling you right now, some of your homeworks are trick questions where it starts you off at um it starts you off as like n is equal to 0, but then you'll have like a n plus 1 or something like that. Again, a series converges when the sum approaches a number as the terms are added and diverges when the sum does not approach a number. So write the first 4 terms of this sequence defined here. We have the top and bottom. So 1, that becomes a 0, and then 1's here, so 1 squared. So it's going to be 1 over 1, which is just 1. Then we have -1. Here I'm going to do in parentheses just so it's confusing. Of 2, which 2 minus 1 is 1, over 2 squared, which is -1 over 4. -1 squared over 3 squared is just 1 over 9. And then lastly, -1 to the power of 3 over 4 squared, which is just -1 over 16. So we can see here that this sum technically does, this sequence technically does approach a number. It approaches 0, right? It's going to keep getting smaller and smaller. But the sum we have at this moment, no proper indication of what the sum is going to go towards. We can maybe start to visualize it, but I rather let the homework do that and skip to the actual solving of it. So the type of sequence that was written here can be more or less noted as a geometric series, where we see that we start off with the base term and there's a multiplicative product that keeps happening and keeps alternating. Actually, this is not a geometric sequence or series. It's a sequence that I want to say in 4.5 we'll learn better about how to establish the limit here, but I think I misspoke. This is not geometric. We're going to get into geometric right now. A geometric series is an infinite series of this form, where you start with some base a, which is your first term, and some common ratio r. The series converges if that r turns out to be less than 1. Then the sum of the infinite series is given by a over 1 minus r. Find the sum here. Now, this is posed as a trick question. Because, or not a trick question, a tricky question. Because, I'm going to take all my losses, because this is not written like this. We don't have some constant multiplying some other variable or some other number to the power of n. But we see that we have powers of n here. So we can just use common algebra to manipulate this a little bit. So one thing I see is that both the top and the bottom can be expressed purely with powers of n. The top can be written as 5n times 5 to the power of 1 over 7n times 7 to the power of -2. At that point, you can technically factor out the 5 and the 7 to the power of -2. You have the sum Well, I think I factored that out a little too curious. I mean, you could factor out like that. There's actually no harm in that technically, um, but for here, I'm just gonna factor out just out of this fraction first because we're gonna see that we need that constant. So the sum of by 1 over 7 to the power of -2 times 5n over 7n. We know that's just the distribution of power at that point. So we can literally just rewrite that as 5, 1, 7, -2 times 5 over 7 to the power of n. And then the last thing that we don't have to do, but we should do, is we should make this normal, because that looks ugly. And there, everything's a variable. I mean, everything's in a digit, so we know we can simplify that. So 5, and then that's negative exponents of 5 times 7 squared, which is just 49. And I think that's going to be, it's going to be 245. Let me find out. So, yeah, 245 is equal to 245 times 5 over 7 to the power of 10. So now we've set it up as this format. And we can see here that we can build this sum. Why? Because the absolute value of r is less than 1. It's 5 over 7. 5 over 7 is definitely less than 1. So we can set that up. Let's go ahead and set that up. Says 245 over 1 minus 5 over 7. That's going to simplify to 2 over 7. That's not even, so I'm just going to go ahead and put the 7 on top. 245 times 7, that's going to be 1,715 over 2, or 857.5. And that is your sum. Now, granted, we were only allowed to do this because the absolute value was less than 1. Remember, a key caveat is that when we're told that this sum exists is because it does converge, right? So it converges, the sum exists, so therefore the sum must be some number. Does that mean that a sum doesn't always exist? Yes and no. It depends on what series you're looking at. We're dealing with a specific geometric series, and in these geometric series, they have this shortcut with their sums. So please keep that in mind. Let's go ahead and move on to the last page. So last page basically goes over the rest of the detail. Convergence and divergence of a series. How do we add up an infinite number of values? Add up the first k terms. This is the kth partial sum of the series. So sk is then equal to this. And this would technically be like a forward value of like, well, S1, S2, S3, etc. But this is the way that we're going to take the infinite sum of that. This is now a limit. The sum of the series is the limit as the number of terms being added increases. So we can rewrite this, which is what we're trying to figure out, which is the s without a subscript, as this. When the limit of a partial sum exists, the series converges and its sum is L. When the limit does not produce a number, the series diverges. Again, when we're talking about using this sum, we need to keep in mind that we're considering this series to be convergent. not the whole expression itself. At one point, we're going to start looking at when the sums converge, but right now we're just paying attention to the A's, not the S's. Okay, so please keep that in mind. Let's go over another thing that is going to help us practice this. A telescoping series. A telescoping series is an infinite series where many terms cancel when you write the partial sums. If the partial sum, if an is equal to one entry minus a following entry, the partial sum can be written here, where eventually we start seeing that these terms cancel each other out, and you're just left with b1 minus bn plus 1. Thus, when you take the limit of that Sn, you're really splitting it from here to here, and then because this will be a constant that doesn't need the variable n, you will jump it to be b1 minus bn, or I'm sorry, the limit, so n goes to infinity, of bn plus 1. If this limit exists and is finite, the series converges. Use a limit to find the sum of the series. Find the kth partial sum limit. So let's start here. And again, we have that technicality. We do not see if this how this works right away. But we're going to use the idea of a telescoping series to figure this out. And we're also going to use something we reviewed, partial fraction decomposition. Recall that this is just a factored expression on the bottom. And this factored expression on the bottom must equal sum a over n plus sum b over n plus 1. You get 1 is equal to an plus a plus bn. This is from multiplying the divisor, okay? And then you solve for your a's and your an's. We can see here that because it's the only constant, a must be equal to 1, and a plus b must be equal to 0. If a is equal to 1, then b must be equal to negative 1. And thus you have this that can be written as 1 over n minus 1 over n plus 1. And here you have this process occur. Now, in order to best see this process, we should definitely do it because we also don't know when our series are starting and technicalities among that nature. So first thing I'm going to do is actually I'm going to go ahead and I skipped a step. I forgot to write as a limit. K goes to infinity and replace infinity with that k. One over n plus 1. So I'm going to split this expression to be 1 over n minus 1 over n plus 1. And then I'm going to start writing this out just a little bit, just so I can see what I'm dealing with. So limit of k goes to infinity of this whole thing. I'm going to write first 1 over 1 minus 1 over 2 plus 1 over, now when n is 2, 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And I'll keep this up, and because I'm doing a k term, even though I'm taking a k to infinity later, I'm going to go and do it up to k. So I have, actually I'll do k minus 1. 1 over k minus 1 minus 1 over k. Right, and then plus, now, here, I'm gonna label this because I feel like this is not the best labeling. N is 1, n is 2, n is 3, n is k minus 1, and n will be k here. So it'll be 1 over k minus 1 over k plus 1. And you technically have taken out every middle term except for the first term, 1, and that term, the k term, minus 1 over k plus 1. Well, we know that we can, from here, just move the limit. So 1 minus the limit as k goes towards infinity. 1 over k plus 1, that's bottom heavy, so that's just going to be 1 minus 0. The answer is 1. So if the sum is 1, then the series, I was going to say converges, the series converges. Okay, so let's do a technical recap. So we're learning what these sequences and series are. We're messing with them in this section over here, and we're kind of just approaching what if these limits exist. And we're doing these limit notations. Okay? So we're practicing stuff from Cal 1. Now, as you do these limits, the notation, although it may have n or k, is going to look very similar. But the question now, instead of take the limit, has become, does the sequence converge or diverge? Which has a very technical difference, right? Because converge, it's missing all of that extra limit part. And I mean, converge, diverge, it's missing that limit part. So please keep that in mind. We're evolving the language. And then we're talking about an infinite series. And we're talking about how we also know a series converges when the sum approaches a number as the terms are added. It's also going to be into that later with the whole definition of a limit. And we're going to start seeing the integration connection here as well. But right now, I would argue that we're going off course a little bit, but we're going to like collide back into our main line. But I promise this is this is maybe not how other classes are doing it, sure, but this is like on book material. But it's just, I prefer this way of going about it. So humor me in that. 4.2 again talked about taking an infinite sum and saying that now paying attention to the sum, we could find out if it converges or diverges. Paying attention to the sum and seeing if the sum approaches an actual number and versus not approaching a number at all. So here we see that this is going to eventually converge because the sum approaches 0. Here we see that this will eventually converge because we know the sum approaches an actual number, not like an infinity or it just exists, period. And then the idea of arbitrarily adding these numbers with the notation of limit. Because this is easier to do. Because if you have this, that's a bit too arbitrary. You're just adding numbers and making it work. Doesn't make sense. If you take the limit and then you mess with this first, and then let k be that thing that infinitely increases, and you can use what you've learned from Cal 1 to see if this sum is either infinite or it equals some exact number. So keep that in mind because this problem is not, it's written easy here, sure, but it's not easy. It's very technical. Okay. Um, Let me see. Let me see. And again, this also doesn't infer that, like for example, this series, it does not infer that this limit, I mean, this series will necessarily converge to one. It's the technicality of when the limit exists, the series converges, but it doesn't mean that it converges to one. Here we saw, um, here we saw that it does converge to zero, and it does converge to infinity. So keep in mind of those little technical differences. Um, let me see. Is there anything else I want to say? Do the homework because that's gonna practice a lot of that terminology and trying to tell the difference between everything. Um, um, yes, that's gonna go ahead and stop us for today. Um, I mean, for here, for example, we know that that converges to. Let me see. That's gonna converge to zero because I mean, just quickly you can rewrite that here. I'm gonna do it in different color because it's not important to this part of lecture, but I'm just adding, that's going to be 1 over n squared plus n, that's bottom heading as n goes towards infinity. So we know that that converges to zero, but the sum existing is its own little hint, its own little tidbit. So you may get asked to prove convergence because the sum exists, or prove convergence because the sequence limit exists, and things like that. So just keep that in mind. Um, I'm not giving you a homework 4.2 because 4.2 and 4.3 are very intertwined. So I'm just going to go and delay that. You'll have a 4.1 homework. But if you feel uneasy, I recommend you try to do the group work by yourself before watching the video. And then you watch the video, and then you'll see what hits and what doesn't. Okay, guys, that's going to end today's lecture. Let me know if you guys have any questions. I'm trying to catch up with grading. Um, but yeah, let me know if you have any questions. I'll see you on next one. Bye bye.